A couple of housekeeping notes to begin with. We are recording this webinar, so please mute yourself, keep your camera off until our Q&A portion. We will be sharing this recording out to everyone who registered, as well as posting it on our YouTube channel afterwards. We will have time for Q&A at the very end of today's presentation. So please hold your questions until then if you'd like to share them out loud. But if you'd like to pop any questions in the chat while Darren and Yog are presenting, please feel free to do that throughout the presentation. I'm going to give you just a quick overview. And I should say that I'm Jess Delfiaco. I'm the Communications Manager for the Midwest Climate Adaptation Science Center, or the CASC as we call it. And I'm going to tell you a little bit about who we are and what we do, and then we will get to introducing today's speakers. So the Midwest CASC is a partnership between the USGS and a consortium of institutions throughout the Midwest region. You can see them up on the screen on this map here. And it is hosted by the University of Minnesota, Twin Cities. That's where I'm based, and several of our staff members are based. We are actually part of a national network of these CASCs run by the USGS, all of which that work to produce science that can inform resource management efforts and help fish, wildlife, water, land, and people adapt to a changing climate. We accomplish that mission in several ways. We conduct synthesis research on regionally relevant topics. We host capacity building workshops and an annual gathering, which I'll share more about in just a moment. Of course, we fund climate adaptation research projects and partnerships with the USGS, and again, going to share more about that in a moment. And we support a large network of graduate students and postdoctoral fellows who are doing research in this space. As I said, we do something every year called the annual gathering. This is when the entire Midwest CASC community, which includes our staff, our research teams, our partners, prospective partners and PIs, and community members coming together at one of our institutional members to share research and get to know each other and kind of kickstart collaborations. This year, we're going to be in East Lansing, Michigan, hosted by Michigan State University, and registration is now open. So if you are on this call, we want you there. Head to that link to learn more and register if you would like to join us. Second announcement is that, as I mentioned, the USGS funds climate adaptation research projects through the CASC, and their annual project solicitation process is open right now. Anyone who is affiliated with a Midwest CASC consortium institution, so if you're on that map that I shared earlier, or if you are affiliated with the USGS, you are eligible to submit a statement of intent for a project, and those are due in just a couple of days. So hopefully this isn't the very first time you're hearing about this, but whether this is new to you or you're working on an SOI, please feel free to reach out to us directly with any questions or visit that link on the page. I'll also pop it in the chat to find the landing page with all of the details about this process. I think that is then it for me. Jessica Hellman is going to talk a little bit about the CAP program. Jessica, go ahead.
Hi, Jess. Hi, everybody. Hey, am I the only person who lost your slides? I don't know where they went.
I can still see the slides. Yep. Slides are still visible.
Slides are still visible. Okay.
I can stop and reshare here and maybe that'll fix it.
Maybe it's just on my end. That's definitely possible. Ah, beautiful. Maybe.
Maybe. Are we on the right slide? Are you seeing the CAP Fellows program slide?
Yes, now I'm see. Yes.
Okay. Great.
Thank you very much. All right. Hello, everybody. I'm Jessica Hellman. I am the consortium, the director for the consortium of the Midwest Climate Adaptation Science Center. And it is my privilege to introduce our speakers for today, our presentation. And before I do that, I want to give a little bit of context of who these speakers are, because they are part of a really interesting program that exists nationally across the CASCs. And that is called the Climate Adaptation Postdoctoral Fellows Program, or what we call CAP Fellows, Climate Adaptation Postdoctoral Fellows, is hosted by the National CASC. It brings together postdoc scholars from all around the country to conduct independent research and research that's tied together and collaborative. So they're all working on a common theme each year, and all of the themes relate to the CASC mission. So they're working on climate change impacts and adaptation science related to fish, wildlife, ecosystems, and people related to natural resources. Each cohort, each fellowship forms a cohort. It's 2 years long. It's centered around a common climate theme, such as wildfire was one. This is what we call the future of aquatic flows. And through that program, they conduct management relevant research, just like we do generally in the CASC, but also receive training and professional development about how to be a management relevant scholar and how to work collaboratively and bring their ideas across the entire national network. In fact, we will soon be launching the next CAP Fellows cohort topic. It's called the Future of Species Range Shifts. This one is actually going to be organized or hosted by the Midwest region at Indiana University. Indiana University and Gabe Filippelli has been taking the charge of getting this cohort organized and its theme articulated and its program built out for the participants. It will start in 2025. The grants to support those fellows are just now being finalized. So that's something to look forward to. Meanwhile, our speakers today come from the current ongoing CAP Fellows program. These are our Midwest representatives. Dr. Darren Ficklin, who I'll introduce, is the mentor or the advisor in this relationship. And Yog Aryal is, forgive me for that terrible pronunciation. I'll see he's a spectacular scholar here in a moment, that he is the postdoctoral fellow. And this cohort program is not only for the fellows, but also for their advisors. So it's a really interesting opportunity for both. So I'd like to introduce both of them quickly on background and then turn the mic over to them. So Dr. Darren Ficklin, he's an associate professor in the Department of Geography at Indiana University. He was the person to put forward a proposal that won our region to be able to serve as the advisor in this special CAP Fellows program. His research focuses on the impact of climate change and variability in the hydrologic cycle, specifically in agricultural and in mountainous regions around the world. He currently works on things like assessing the impacts of climate change on snowmelt and stream flow, determining the spatial and temporal trends of drought in the United States, and examining how aquatic species and aquatic habitats change with climatic change, and often does a lot of stream temperature modeling. Dr. Yog Aryal is the future of aquatics flows, the postdoctoral fellow, also at IU, working with Darren. He focuses on how climate change affects watershed hydrology and droughts, is a PhD from the University of Wyoming. He's worked as a researcher both in the US and in Nepal, and his current project, which we'll hear more about, explores how changes in snow processes and their drivers impact hydrology and ecosystems in the Great Lakes Basin. Something of regional significance, but also national importance. He is also working with collaborators across other CASC centers. I understand there's some co-authorship working there, some collaborative paper writing that's going on among the whole cohort, and that group is collectively working to understand how we could be doing water management better in the face of climate change. We're very excited to hear these presentations, and grateful that the two of you would join us today, and for everyone on this call to have the opportunity to see what the CAP Fellows program is all about. So I will turn it over to the two of you.
All right, thank you. Let me just share my screen. How does that look? Can you?
Yes, I see it.
Good?
And
Good,
I
looks
seem to
good.
be the
No.
one with difficulty seeing things, so that's a good sign.
Good. Well, thank you for that introduction. You've done all of the hard work, introducing what we're trying to do and what we're trying to accomplish. So I'm going to give the overview of what we're doing, where we're at in the project, what's left to be done, and then Yog is going to share his screen and do some more detailed analysis of what he's been working on the past couple of months. So this is a kind of a perfect time to give this presentation. This is kind of the inflection point where we're starting to produce gigabytes, terabytes of data. And we're kind of interested in what people want to see out of this project. So as was mentioned, this project looks at how rain on snow events are going to influence streamflow, aquatic species management, and stream temperatures throughout the Great Lakes Basin. If for some reason you do have a question and we can't get to it, just feel free to send us an email. Happy to chat outside of this as well. So before we get going on what rain on snow events, or before we get going what we're trying to do with this project, let's introduce what a rain on snow event is. It's pretty much exactly what it sounds like. It's rain on snow. It's when you have liquid precipitation on a solid snowpack. They largely occur when warmer rain falls on an existing snowpack. And the importance for us and for species is that this really results in a rapid export of runoff and snowmelt. If you've lived in the upper Midwest during the spring, you've seen rain on snow, and you've probably seen that tied with floods quite a bit. So their severity not only depends on the magnitude of the liquid warm precipitation event, but also the elevation of the freezing level. You can imagine if you're at high elevations, the snowpack is going to be more frozen than if you are at lower elevations. Great Lakes Basin, we don't necessarily need to worry about that because elevation is not necessarily the biggest deal. This is more for the Western United States. It also depends on the snow water equivalent. And if you're not familiar with snow water equivalent, or SWE, this is basically you go outside, you grab a snowball, you put it in your microwave and you melt it. Snow water equivalent is the amount of water that comes when you melt a snowpack. Not all SWEs are the same from event to event. They change depending on the humidity, the climate, the spatial resolution, etc. So that does change from event to event, the amount of water within the snowpack. And of course, it also depends on the spatial extent of the snowpack, where the snowpack is, whether it's just in the valleys or the high elevations. That determines and dictates what type of flood event that you have. So on the right is probably a diagram you've seen before in a lot of your introductory courses or on the Weather Channel. These are the four types of precipitation. You have rain all the way to the left and snow all the way to the right. What we are interested in this particular project is that yellow-orange triangle, the warm air mass that comes in. Essentially what this is doing in rain on snow events and how that occurs is that this warm mass comes in when you have a snowpack on the ground. The snow that comes out of clouds gets converted to liquid precipitation, lands on the snow. So we're interested in this now, but we're also interested in how this is going to look in the future. So if you think about what this warm air mass is going to do in the future, the air is going to be warmer. We expect this yellow-orange triangle to kind of go over to the snow domain quite a bit and go back and forth. So we expect rain on snow events to be more frequent in the future. Yog will talk about whether that's the case or not. Okay, so where are these and how many exist per particular year? So on the left, you have average seasonal rain on snow from 1960 to 2009, and on the right, you have the standard deviation of these rain on snow events. You can see the Western United States, we're looking, and Western North America, we're looking anywhere between 10 to somewhere up to 20 to 25 to 30 events per year. So it's a substantial amount of rain on snow events. This is why the Western United States has been studied quite a bit when it comes to rain on snow events, because they are there and they exist and they do a lot of damage when they happen. But they also exist out in the eastern United States as well. We're looking at northeastern North America, eastern United States, 10 to 15 events. Those are kind of the bigger events. But if you zoom in on the Great Lakes Basin, they certainly exist in this region as well, especially in the northern portion of the Great Lakes Basin. Anything blue in this case indicates 5 to 10 events. Yellow is 10 to 15 events. So they do happen here, and it's something that we do need to be aware of and study as we move forward. So why should we care about rain on snow event? Well, the simple answer is just flooding. You'll see if you open up your browser or newspaper, if you still get newspapers or open up your news browser, you'll see these news articles all over the place. This is in Tahoe, where rain on snow causing flooding on South Lake Tahoe roadways. Up in Maine, rain's melting, causing flooding. This is in Detroit, melted snow combined with rain floods neighborhoods in Wayne County in the Great Lakes Basin. And here for NPR News, melting record snowpack rain expected to cause flooding. So again, if you live in this particular region and you're paying attention to the weather, you probably have seen this rain on snow and its connection to flooding. It's also been studied quite a bit in the literature as well. This is the paper that was published in Nature Climate Change by Keith Musselman. I would consider this one of the keystone papers in rain on snow, where they looked at the increases and shifts in rain on snow over the Western North America. This is a more recent paper published in Water Resources Research, looking on the role of rain on snow and flooding in the conterminous United States. This is more of a European-focused study, where they look at a large-scale analysis of rain on snow events with these potentials. So it is studied quite a bit. Most of the studies that have occurred on rain on snow largely have occurred in the Western United States for obvious reasons. Lots of snow out there, lots of people. And from that Nature Climate Change paper by Musselman, this kind of shows what we expect for rain on snow in the Western United States. Yog is going to present more on the Great Lakes Basin and what we expect for this particular region. The left column is total volume, the spatial extent, and the intensity. Green indicates an increase in all of these variables. So what we're seeing is we do expect an increase of volume, spatial extent, and the intensity of these rain on snow flood potential events. On the south side, the southern portion of the United States, you see actually decreases in these events. That'll come into play when we start talking about the transition from rain to snow to rain in the Great Lakes Basin as we move northern in latitude. So we do expect, at least for the Western United States, that this is going to cause more flooding in the future. What this means for the Great Lakes, we'll talk about that here in a bit. This is an article that came out a few months ago, not necessarily related to the Great Lakes Basin, but it certainly caught my eye. And this was on rain comes to the Arctic with a cascade of troubling changes. So the Arctic region, it doesn't rain that much. Doesn't rain on snow that much, I should say. So all of these, the indigenous peoples, wildlife, ice loss. There's a lots of things going on in the Arctic that we just don't know what rain on snow is going to do. So a lot of the work is certainly going to start heading to the Arctic and what these rain on snow events are going to do for this particular region. But that's not it. Flooding is certainly one of the things we're going to produce for this particular work. But the kind of the niche or the hypotheses of this particular work is a couple different things. One is that we think that rain on snow events might increase the susceptibility of spring and summer droughts. And the hypothesis is that when you have these rain on snow events, this results in really a rapid export of water out of your watershed into your rivers. This is water that is rapidly exported when this is normally water that is slowly melting and slowly trickling into your soil system, your soil column, and your water table. This water eventually makes its way back to the streamflow in late spring and late summer. When this water is rapidly exported out of your watershed or through your rivers, that water is not there to sustain some of this streamflow during the summer. So that's kind of the hypothesis that we're working in. So rain on snow melt leads to runoff and flooding, leads to decreased water storage. And we think that might lead to summer hydrological drought, and Yog has some results or some preliminary results that look at that. We're also very interested in temperature in the Great Lakes Basin. Anyone that's went salmon and trout fishing in the Great Lakes Basin knows that water temperature is super important for these particular species. So we're also going to look at how rain on snow influences these seasonal water temperatures. We don't know what this is going to do. This has not been studied in detail really anywhere. So this might be one of the first studies that's going to look on that. So on the left is the spring and summer season. On the right is the fall of winter. And I really just want you to concentrate on these top boxes where the snow melt, we think, largely decreases water temperature in spring and summer, while surface runoff increases water temperature. That makes sense, right? If you have a really large pulse of snow melt entering your river, that should decrease your water temperature. So some of the water temperatures that we look at in the Great Lakes Basin are sustained by some of the snow melt that keeps them cold. When that's not there because of rain on snow events, what does this water temperature look like in the future? Quite simply, we don't know, and that's something we're working on. So why are we interested in stream temperature? I kind of already tease that a little bit, but stream temperatures determine biological and chemical processes, nutrient cycling, algal blooms, the presence of algal blooms, the presence of bacteria, fungi, the transfer of semi-volatile compounds, and aquatic habitat. The aquatic habitat is really what we're going to look at in this particular study. Warm waters are more biologically productive, but that's not necessarily a good thing. The species that flourish there may be undesirable. I'm thinking about these invasive species that are all over the Great Lakes Basin. Future water temperatures may be more desirable, maybe more productive for these particular species and not the species that we want to live there. When you have this competition, this may result in a cold water species decline because you have several species fighting over the same amount of food. Talking about invasive species pushing these cold water species out. And as we know, fish don't have legs. They can't just get up and move out of the stream and head to another one. They got to figure out to adapt in these conditions, and some won't be able to. So this kind of brings and wraps all around where we're headed with this project. We don't know, the magnitude of these changes are unknown for the Great Lakes Basin. So the question is, what influence does climate change have on rain on snowmelt, hydrology, and stream temperature, and their influence on aquatic species in the Great Lakes Basin? So what we did for this project is we developed a really large-scale hydrological model. On the right is one of the older models we worked with. I'll show you some other results. This is one of the models that my PhD student created. So we're modeling the entire Great Lakes Basin. It's a big computational task, which I'll go over here in a bit. So we use the soil and water assessment tool. I'll introduce that. This particular hydrological model had a lot of deficiencies, which we tried to fix for this particular project. We added rain on snow, and we coupled it with water temperature. I'll talk about that here in a bit as well. To make sure that this model works, we calibrated it and validated against 238 streamflow sites. I'll show you a better image of that here in a second. And 74 snow water equivalent sites. So we did a lot of heavy duty calibration to make sure that this model works, to make sure it's accurately doing what we want it to do. We're working on the stream temperature calibration right now. So as I mentioned, on the right is my PhD student's model of this. Yog actually produced a more high resolution model of this, but to get an idea of what this looks like, if you zoom into Michigan, this is the resolution of the model. Every single blue line that you're looking at is a river that we're modeling in this system. Every single light gray bordered polygon in the back is the sub-basin that we're modeling in this. So the blue lines will give us stream temperature, stream flow. The white and gray polygons will give us snowpack, snow height, all of the evapotranspiration, all of the kind of the land surface variables. So pretty high resolution stuff we're building. So if you're not familiar with the SWAT hydrological model, this is a USDA based model. The USDA built it, maintains it, constantly updates it, and they're good at kind of helping others adapt and improve this model. So quite simply, we're estimating the water balance equation. This is the water balance you learned in hydrology or intro to environmental science, and that's kind of shown on the right, where we're estimating these different variables every single day. The way that SWAT does the hydrological modeling is it uses the concept of hydrological response units. A hydrologic response unit is just simply a unique combination of land use, soil type, and slope. You overlay these in kind of a GIS format, and where you have a unique combination of these, you then estimate the water balance on these unique combination of these spatial units. So I'm showing you kind of a schematic of what this looks like where for the Great Lakes Basin, where each sub-basin has 3 HRUs. In reality, each sub-basin may have tens to hundreds of HRUs. So the more you add, the more complex it's going to be. And then the water is just routed throughout your system. The Great Lakes Basin is not one outlet like the Mississippi River Basin is. There are many, many outlets that flow into the Great Lakes. So this is done for all over the Great Lakes Basin. So the original SWAT model did not simulate rain on snow events. So that was a big miss with this particular model. The snow melt was just simply done by temperature. When temperature rose above a particular temperature, the snow pack started melting. That melt would then enter the river system. Nothing to do with precipitation was in the original model. So my old PhD student, incorporated a snow melt routine into the SWAT model that involves several variables other than air temperature, such as precip, wind, saturated vapor pressure, and atmospheric pressure as well. And this was taken from the Snow 17 model developed by NOAA and we incorporated this into the SWAP model. This shows, just to give you a little bit of confidence, this shows that what we did actually worked. This was published in 2021, and Yog is doing this exact module right now. So what you're looking at here on the left is Nash-Sutcliffe coefficient. You don't need to know anything about this coefficient, but anything that's positive and more towards 1 is better. That's an easy way to explain it. On the right, you're looking at snowpack mean absolute air. Anything more towards 0 is better. So we took a lot of these parameter sets and we saw how the model performed with this new rain on snow module in the red. And as you can see from these different plots, is that the model did much better just by including this rain on snow event. This is that was certainly helpful, and one of the reasons why we applied to this is that we wanted to test this out again. So the model is doing a lot better just by incorporating rain on snow into its module. Forever ago, I developed a stream temperature model. 13 years ago, I developed a stream temperature model in the SWAP model. The original SWAP model only had stream temperature was only a function of air temperature. So whatever the air temperature was, it's just a function of stream temperature during that particular day. Not super accurate. We know that stream temperature is really a component of all of the hydrology flowing into the river. It's a component of the air temperature, the solar radiation as well. This is kind of showing you just a quick schematic of what I developed forever ago. And it's more hydroclimatology based stream temperature model where the snow melt is incorporated into the model, the groundwater is incorporated in the model, the overland flow or the surface runoff is incorporated in the model. Each of these have a particular water temperature. Basically what this model does is it collects all of the water that's entering a river in a bucket, mixes it around, that water then gets dumped in the river. Each one of these components that go into the river have a particular temperature signature associated with it. And again, just to give you a little confidence about this model, we tested this out in the Pacific Northwest quite a bit. On the left is the Tolt River, and the Pacific Northwest is on the right, the Fur Creek. The black dots indicate a linear model that was already in SWAT, and our white dots indicate the updated model. And as you can see, we are much more on the one-to-one line. So we're pretty confident that we're doing what it's doing what we want it to do. So the issue with dealing with these large scale models with all these complex components is that it is tough to calibrate. It's tough to run the model. So probably the computer that you're watching the Zoom on is not really able to run this model. So we needed to develop these algorithms to run this model. Again, on the right is showing you the resolution of this model that Yog developed. Pretty high resolution stuff. So non-parallel calibration is not feasible. And if you're not familiar with the concept of parallel versus non-parallel is just simply you have one model, you give it some instructions, the model does these instructions, produces output. The parallel algorithm, basically you have multiple models, you send out multiple instructions and it runs at multiple times in the same instance, much faster. So some of these models that we're working with, you have to calibrate 500, run the model 500 to 1,000 times. Imagine doing that once and then twice and then 3 times. The parallel allows us to do it multiple times at once. So we developed this algorithm to kind of handle this problem. It allows us to run multiple models at once and gather statistics and then perform additional simulations. This simply what it looks like in a schematic form. This was all done on the big red supercomputers here at Indiana University. Like I said, you're not going to be able to do this on your laptop or even a desktop. So we have this hydrological model, the Great Lakes Basin. We then distribute this model to several high performance computing clusters. Think of these as just computers, right? We distribute these models to all these different computers. We run the model. We test with the objective functions how well the model is doing. We then have new parameter sets that we input back into these models. So this is showing you kind of 4 different models. In reality, Yog is doing like 20 to 25 different models at once. So this allows us to do some really high computational work much quicker than it would be on a non-parallel system. And really what we're trying to do here is make sure that these calibration statistics, R-squareds, mean absolute error. In this case, I'm showing you the Nash-Sutcliffe coefficient. Any value towards 1 is better. So this shows you the mean Nash-Sutcliffe of all of the observational streamflow gauges throughout the Great Lakes Basin. On the right is showing you the standard deviation. So the goal of this algorithm is to increase the mean national cliff of all of the observation gauges, while at the same time minimizing the standard deviation around this mean. So the goal would be to do it as achieve as best statistics as we possibly can. And as you can see from this figure, the model is increasing the national cliff every single run. You can see it going up. At the same time, the standard deviation is going down. This is what we like to see. And this is some results from Yog's model. On the left is a new statistic. Anything towards 1 is as good as it gets. And on the right is snow mean absolute error. Anything towards 0 is as good as it gets. So Yog did 238 sites for this particular model. So if you count out all those dots, there's 238 dots. And there's 74 snow water equivalent sites on this. And you can see anything above about 0.5, 0.25 is considered good. Mean absolute error, again, the lower you get, the better. So we're pretty confident that the model is doing exactly what we want it to do accurately. So then we can do all these land use scenarios, climate change scenarios. We can do a lot of stuff with this model now that it's calibrated well. So what's next for this particular model? Now that the hydrology is calibrated, we're starting to work on the stream temperature calibration as well. We're starting to put climate projections into this, which Yog will introduce. This will allow us to produce this trout and salmon habitat. It's going to allow us to have results and a website. And we're working with this. We'll start working with this now that we're producing a ton of results. We're working with the Little Traverse Bay bands of Ottawa Indians and the Shed Aquarium. I believe I saw Karen Murchie on here earlier. We'll start to pass results around. What's the best way to disseminate this information? We're now at this point in the project to start doing that. So that's kind of where we're headed with this. And as far as water temperature, so what do higher water temperatures mean for fish? Anyone that's worked in fish in the past realize that fish have some kind of an upper thermal tolerance to where they're happy. And when this upper thermal tolerance is eclipsed, they got to move or they have to change habitats. This is showing you some previous work from my postdoc, where we had stream temperature on the X, cumulative probability on the right. For the historical in the black, the 250s in the blue line, and the red line is the 2080s, and the hatch just kind of the uncertainty around that. So we can develop these cumulative probability curves, and then we can overlay all of these weekly upper thermal tolerances for salmonids or whatever species. I know that the Great Lakes Basin is starting to introduce other types as well. So we can basically determine, how much more time is the upper thermal tolerance going to be eclipsed with our model. We can develop maps. We can do all sorts of stuff just by knowing what habitat fish like to be in and what they don't. This was some work that my master student did about 5 or 6 years ago in the Mobile River Basin in the South. This is something we want to do for this particular project. On the left, we have 88 native fish species, as indicated by those red dots. Those are overlaying on it's kind of a stream flow, but also stream temperature GIS data set from the model. And on the right is where basically you can throw money into these rivers to mitigate some of the influence of climate change or restore the habitat for these native species. And as you can see, the historical is shown by this purple line or red line. You can see that's where we should throw money to save the most native species. This will expand in the future, as shown in the yellow line. It's going to expand in the future, which does give an idea of where we could perhaps nip this in the bud before it gets too bad to throw money in. So as I mentioned, this was kind of where we're at in this particular project and where we're going. If there's something you would like to see, we can tell you that we can do it, or we can tell you that we can't do it. But that we're at the point, as I mentioned before, we're at this kind of this point where we can start to gather information of what's the most useful for this particular region and the people within it. So with that, I'm going to stop sharing my screen. I think Yog is then going to bring his up for his quick presentation, and then if you have questions, I'd be certainly happy to answer those. So thank you.
Thanks, Darren. Yog, are you ready to go?
Did we lose it? Oh, there he is.
Okay.
It looks right.
That's right. That's good. Yeah. Hello, everyone. I'm Yog Aryal, postdoc at the Indiana University. Uh, yeah. As Darren said, we will look at the relationship between the rain and snow melt event or RS event and the stream flow dynamics in the Great Lakes Basin. Our main question of this project is how will change in RS event alter the stream flow in the Great Lakes Basin. These two mechanisms, Darren has already explained this mechanism, and this is our study region. Mostly this region in the northern part, it is forested region, and in the southern part, it is developed or urbanized region. Now, we use short hydrological model to simulate the RS event and associated melt and stream flow and stream temperature. We use the daily maximum temperature, minimum temperature, and the precipitation from this linear data, and daily flow from United States Geological Survey, USGS, and Environmental and Climate Change Canada. We first examine the historical characteristics of the RS event in the Great Lakes Basin from 1916 to 2019. Based on our short model simulations, we define a RS day as any day with over 1 millimeter of rainfall or liquid precipitation, at least 1 millimeter of snow water equivalent present on the ground. Our analysis show that in the southern reach of the Great Lakes Basin, the southern reach of the Great Lakes Basin experienced the higher frequency of the winter and spring RS days during this period. However, when we look at the intensity of this RS event, the intensity is defined as the RS defined as the RS. Okay. However, when we look at the intensity of these RS events measured by the amount of runoff generated from these RS events, we found that the southern and eastern part of the basin exhibited the highest intensity. Interestingly, our simulation showed that RS melt rate can be more than the double of the rate of the regular temperature-driven melt rate. This rapid melting during the RS events is driven by the combined effect of warm rainfall and air temperature. Despite this accelerated melt rate, RS melt contributed only 25% of the total annual snow melt quick runoff across the basin, even though it accounted of nearly 40% of the annual snow melt volume. This discrepancy suggests that while RS events can lead to intense melting, the resulting meltwater runoff is less efficient at generating steam runoff compared to the gradual temperature-driven snow melt process. Next, we look at the projected change in the RS event characteristics. We use the CMAP6 model 2045 to 2074 under moderate SSP 37 emission scenario, we see some notable change in RS event characteristics. First, across most of the Great Lake Basin, first look at the temperature for climate projection from these models. Mostly temperature and the temperature is projected to increase as the total rainfall is projected to increase. However, the spring and snow rainfall shows increase in the northern part of the basin, but decrease in the southern part of the basin. If we look at the RS days across most of the Great Lake Basin, our simulation point to decrease in the number of RS days in the southern part and increase in the northern part. This decrease in rain and snow days in the southern and eastern part is primarily driven by an overall decline in snow cover days, but in the northern part, a shift from snowfall to rainfall events leads to the overall increase in the rain and snow days, despite a projected decrease in snow cover days over the region. Now we look at the RS intensity, that is RS runoff generated from this RS event. In line with the decreasing frequency of RS days, we also project the decline in the intensity of RS event across most of the basin. This RS intensity is measured by the amount of RS runoff generated during these events. Next, we look at what is the driving in the change in this, particularly in this RS intensity or rain and snow related runoff. Our analysis shows that the primary factor in a decrease in the rate of the rain and snow melt rather than change in the rainfall rate during RS event. So in summary, the overall picture of the future climate scenario indicates fewer rain and snow days over most of the Great Lake Basin, coupled with less intense rain and snow events. Now, our next question is, what do these projected change in rain and snow events mean for the stream flow dynamics that sustain the Great Lake Basin's ecosystem and community? Our study shed light on some key implications. First, we find a notable relationship between snowmelt rate and base flow efficiency, which measures a proportion of total water yield from a basin that contribute to sustained groundwater base flow. Specifically, our simulation shows that base flow efficiency increased with higher snowmelt rate, since rain and snowmelt was diminished due to it was projected to be less efficient than gradual snowmelt in generating runoff. The projected decrease in rain and snow intensity could potentially reduce the base flow recharge and groundwater contribution in certain subbasins of the Great Lake. We will see this result in more detail later. So additionally, we develop a statistical model to relate summer low flow condition measured as the annual 7-day average stream flow to the timing of RS melt, rain and snow melt events within each basin. Our analysis shows that the covariance of centroid of the RS melt rate, that is defined as the day of the year when cumulative rain and snow melt exceeds half of the annual rain and snow melt. That means when the half of the rain and snow melt occurs, there is a projected decrease in the day of the rain and snow melt. And our question is how this change in the day of the rain and snow occurring will affect the summer low flow. This model, so from this regression model, we use the simple linear regression model. We plot this beta coefficient. This positive beta coefficient implies that the increase in the center of rain and snow melt, that means the later the snow melt, more the summer base flow. And okay. This model showed an inverse relationship, earlier occurrence of RS melt event and therefore earlier depletion of the snowpack that lead to the lower snow stream flow later in the season. With the warming temperature expected to shift in RS melt events earlier in the future climate scenario, our projection point toward a potential of reduced summer low flow across large proportion of the Great Lake Basin. This finding have significant implications for water supply management and ecological impact. Decreased base flow recharge could stress the groundwater resource, while lower summer low flow threaten aquatic habitat and species that rely on the sustained stream flow during the warmest and the driest month of the year. These are the summary from our preliminary analysis. In conclusion, we find that rain and snow melt accounts for more than 45% of the total snow melt over the basin, although it typically occurs for only about 10 days of the year. Rain and snow melt rates are greater than twice the temperature-driven snow melt rate. These have a large implications for the base flow, for the low flow. Compared to the temperature-driven snow melt, rain and snow events show lower efficiency in generating rapid runoff. Future projections suggest a decrease in the intensity of rain and snow event, that is RS runoff, across most of the basin, largely due to reduced rain and snow melt rate. The anticipated early occurrence of rain and snow events and the reduction in RS melt rates are expected to reduce summer low flow in the future. Yeah, these are the preliminary findings. I will stop here and would be happy to answer any questions or explore specific point from this presentation in detail. Thank you for your attention.
Thank you so much. I would love, we have about 10 minutes left, right, Jess? We can open the floor to questions, which can either,
Yep.
you can come off of mute and just ask it, or if you prefer, you can voice it in the chat window and someone will speak it for you. I would love to ask a question to kick off. It's more an opportunity for the two of you to provide sort of commentary. I have spoken many times with a variety of stakeholders about the importance of the rain on snow in our region as one of the sort of major climate signals that we think about. But I appreciate so much in that last slide that it's sort of a transitory phenomenon, as the climate further warms, there could be, your model suggests, fewer rain on snow events. I wonder then, how would you, if you were talking with an interested member of the public or explaining the significance of rain on snow in our region over the long term, what would you say? You'd say it's a major phenomenon right now in terms of generating hydrologic extremes. It's, you know, how would you talk about the fact that it's, sometimes we say like there was pre-climate change and after climate change, but this is something that varies across the intensity of climate change. Does that question make sense, either one of you?
Yeah,
How would you,
tough.
talk about this
Yeah.
notion of how dynamic this process is? Perhaps that's a way to say it.
Yeah, it's tough because rain on snow, you have to have snow, and you have to have the rain precipitation coming as rain. I always like to do the kind of introduction slide that I showed that kind of showed the different phases of precipitation and how it takes to convert one to the next. I mean, this is not an issue for the Western United States because you have elevation that's going to keep things really cold, because rain on snows are going to continue to be a big event out in the West. But here, so some of Yog's work and some of the PhD students, we see that a transition kind of at the middle of Michigan where rain on snows are declining up and above they're increasing. And what that line does, we don't know. I hate to say that rain on snows, we're going to have less flooding because we're still going to have snow. So I don't want to, it's tough.
Yeah, we also have the implications of the long-term, I mean, base flow and the summer low flow due to change in this rain on snow events.
Would you say a little bit more about that?
And this will have the implication for the so groundwater recharge. It is clearly showing that there is a contribution of the change in rain on snow would be likely decreased toward the declining of the summer base flow.
Holly.
Hi, y'all. Thank you so much for those really awesome talks. And as a fish person, I was very excited about the potential applications that you were discussing. And I was curious if you had thought of or already kind of started to work on connecting the increased runoff, especially around the springtime, to like key points for certain fishes. I saw you were working with Odawa, or Little Traverse Band of Odawa. And I know sturgeon is a super important fish for them, and they've expressed concerns over spring runoff and things like that. And it sounds like the data and approaches you've developed would be fantastic for answering those types of questions. So yeah, thoughts on that?
Have we done it? No. I think that's next, and Karen Murchie's on the call, and so she's one of the ones that's going to help with some of these questions. Jason Knopft out of St. Louis University is also on this project. So a lot of these questions I can't answer, but I know biologists sure can. So we'll be producing information that can help answer your question, but what species to look at, what timing of the year, I think we'll be guided in that direction depending on the biologist, fisheries biologist. Yeah.
Olivia's shared. Oh,
Go for it, Jess.
Olivia shared a question in the chat asking, what might we learn from the eastern U.S., where presumably this is rain and on snow events are more common? And then I might expand that to say, how have you maybe benefited or learned from other regions more broadly as part of a national synthesis? How's that benefited your research?
Yeah, as far as the eastern United States, I don't have any idea. Other than, some of the methodologies that we're using is the exact same no matter where you put it. I imagine the eastern United States would be pretty similar to the Great Lakes, as in you have the northeastern United States that's going to continue to be cold and snowy, much like the northern Great Lakes. Maybe Yog knows more about some of the literature review on the eastern United States. Really, most of the work has been done on the western United States on this, but I would imagine you're going to see very similar transition from lower rain on snow events and as you move northward in the northeast. What this means for base flow and stream temperature, yeah, I'm not sure. I'm not sure where we'll land on that one.
The relation between the base flow and the RS met rate is very similar to the Western United States and our Great Lakes region, but I have not looked particularly at So general findings, relation between the timing and the particularly in this study, we are interested in more focusing on the rate of melting. The results are similar in Western US and in our region. And there are some discrepancy based on the land cover type or forested or non-forested, like those things. We have not separated it. We are still working on the results, and we will see how the response of the basin to the rain and snow melt rate depends on the other basin characteristics.
Yeah, and just to add on that, we're not looking at land use change either. Maybe that's something we could do. So we don't know whether forests are being cut down or forests are being grown in the future. That's not part of what this project is doing, but I suppose it's something we could look at.
Another question? I think we have time for one more question. Okay, here's another one from in the chat window. Excited to see what a difference adding rain on snow processes to SWOT made in your model accuracy. Are there other processes you feel are not well represented in hydrologic models right now? Things that could also be important as the climate changes? That's a terrific question. Other things we ought to know better in addition to rain on snow.
Well, I mean, every hydrologist has their baby hydrological model that they kind of defend. SWOT does not do groundwater very well at all. That's one thing that could be approved for this particular model. SWOT has been coupled with groundwater models to do this exact thing. As far as what other hydrological models do and don't do, I mean, some of them lump all of these hydrological processes, and the large scale, they lump all of the processes in just one little square that's, that could be the size of Minneapolis, right? You try to lump all of these processes in a big, large spatial unit. So that you're not going to represent the hydrology well when it's such a large resolution, but you can't get too fine resolution or you'll never be able to run the model. So they all do things well and they all do things bad. I don't know. It's just depending on what model you're interested in. But for particular SWOT, groundwater is an issue that people have been trying to work on. But
Well, on the
it's
computational
open source.
Yeah.
It's open
Right.
source, so you can change it and add.
Well, on the computational challenges in the spatial scale, I mean, frankly, to hear you say that sounds a lot just like climate modeling, right? So that kind of nested approach where you ask, there's a variety of different resolutions at different spatial scales, depending on your needs, and downscaling methodologies and all of those other kinds of things. But I suppose in the climate world, there's an active effort to develop sort of ensemble modeling and model crosstalk. Is that the case in the hydrologic world?
Yeah, it's the same. I mean, they're trying to do hydrological model ensembles. There's all these projects that collects all of the hydrologic models for regions, and very similar to what you do with climate models, where you would average the ensemble or do statistics on the ensemble of climate models. You would do the similar things with an ensemble of hydrological models, because again, they're all just like climate models. They're all doing something good and all doing something bad. So they hope that they're all not doing the exact same thing. So you can average it out and feel good about it.
Great, thanks so much. Jess, you want to take us home in 1 minute?
Yeah, yep, we are at time. So thanks so much, Darren and Yog, for sharing your research with us today. If folks would be so kind as to answer the 2 closing poll questions on your page right now, we really appreciate that to help us keep these going and getting better with each month. We're going to be back in June. Keep an eye out for the announcement of who our speaker will be. And I hope you can join us in a few weeks. Otherwise, thank you all and have a great rest of your Monday.